Okay, well, welcome back everyone. Oh, by the way, I've been informed that in the afternoon coffee break there'll be cake. So, next speaker, Sebastian Velazquez, who's going to tell us about extensions of codimension 1 foliations.
Ahí va. Sí. Hello. Thank you for the introduction. Thank you to the organizers for inviting me to give this talk. It's a pleasure to be here at IMPA, always, in Rio in general. So today I'll talk about, well, extensions of foliations. This is a joint work with Pablo Perrella from University of Buenos Aires. And since I'm the first one, I will start saying what a foliation is, at least to me. So if X will take it smooth, analytic or algebraic variety. And so a foliation will be either a subsheaf of the tangent sheaf. We'll take here the quotient. We'll ask this guy to be closed under the Lie bracket of vector fields. And this guy to be torsion free. Yes. This in general, this is just notation. The double dual of this guy will be the normal bundle of the foliation. This double dual will be the normal bundle of the foliation. Yes. And in general, so just by duality, this guy is equal to some ideal sheaf times this normal bundle. Yes. The ideal sheaf will be the ideal of the singularities of the foliation, which is nothing else than so. Yes, sorry. Yes. Of all foliations will be codimension 1. Yes. So the singularities of F, let's say, will be the points where this guy is not locally free. And so equivalently, this here is given by a 1 form because it's a codimension 1 foliation. And so we'll have some 1 form, omega, in this space. And, well, the fact that this does not have torsion is equivalent to, let's call it the 0 locus of omega, so the place, the locus where this vanishes. This has codimension at least 2. If not, if it had 1, then this guy would have torsion on this codimension 1 locus. So let's do this. This is this. And this here, by Frobenius theorem, is equivalent to omega wedge d omega equal to 0. Yes, so we can, and this is, let's say, an algebraic description of what a foliation is. In general, what we'll have is X, we will have our singularities, will be some points. Through these points, maybe away from these points, we'll have a partition of our X into analytics of varieties of codimension 1. Yeah? And through this point, we will not have that. In general, we'll have a picture like this. Yeah? And so the title of the talk is Extensions of Codimension 1 Foliations. So I'll use this picture. The setting will be like this. X will be, again, I said smooth, will be compact, analytic or algebraic, and this guy will be inside some Y. And the codimension of x and y. X and y is 1, just as the same codimension as the foliation. Yes? And so the question is, okay, I have my foliation f here of codimension 1. And question, when does f extend to a codimension 1 foliation? Let's call it f bar on y. Yes, so when do we have a picture like this? Yeah, so when the ambient space is also foliated in a way that when I intersect this foliation, these leaves, with x, this gives me exactly the leaves. Yes? In terms of this guy, yes, this would be equivalently. The question is, exists? Does it exist an omega in some y, some line bundle? Yes. Let's call it omega bar. Of course, satisfying these two things and zeros of omega of codimension 2, such that I star, so I is the inclusion of x in y, I star omega equals the previous one. Yes?
Seba, do you have a control of the size of y? Or is it compact? Or it's just a small neighborhood?
Okay, good question. The answer is no. A priori, it can be anything, analytic. But we will be able to say more interesting stuff when we know it's compact. No? Like every statement will have like if, and if y is also compact, or if y is algebraic, then we say something better. Why? I'll take your question as an opener for that. Why? Because what we will do is just a priori, if we don't know anything about y, we will look at the formal neighborhood of x inside y. So that doesn't see if y is anything. So we will essentially, we will construct this f bar as a Taylor series. No? We will say like f bar plus t something plus t squared something plus t cubed something. And so that will give us like a formal foliation that extends f. And if we are lucky and maybe we have some other hypothesis on y, we will be able to prove convergence of this Taylor series, and then this will be the defoliation that extends f.
This seems to be local in x. Why do you require that x is compact? Is there some other issue?
In 2 minutes, I will do the local, really like the local picture. And then if I don't answer, you ask me again. Okay, so motivation for doing this is the following. The first thing is like maybe, well, there's a story of defining, so fix some line bundle L. This one we will call L bar. L on X. And we define something that's like fol XL, which are foliations with NF to L. No? We fix this normal bundle. We define the space. This is a quasi-projective variety. And there's like a long-standing story of understanding the geometry of this space. So X is fixed, the normal bundle is fixed, and we look at all the foliations on X with this normal bundle. And this extension problem, what tells us is that, well, so with this in mind, if you have this, you can always restrict a foliation to X. This will give you a rational map like this. No? The loci where this is not defined is essentially where this does not hold, which is the foliations that are tangent codimension 1 to x. Yes? And the point is that you still define a foliation, but the normal bundle is wrong. No? Okay, and so there's been now quite a few, let's say 4 or 5 works, essentially studying this map, yeah, and essentially saying that this is quite surjective, using essentially in these works, y is Pn, and x is either a hypersurface or a Grassmannian or a complete intersection. Yes, just to name a few names. I hope I say all of them. So Mauricio is over there. He did this for complete intersections with Carolina Araujo and Mazzarenti. There's also Mateus Figueira, I think it's not here, but a student of here that did this for hypersurfaces in projective spaces. There's also other works from, well, Benedetti, Faenzi, and Muniz for co-minuscule Grassmannians, also in projective space. So the ambient space, Y is also a projective space. And so, well, essentially, if we do this very well, we will also be able to contribute to this, the study of these maps of restrictions of spaces of foliations. There's a conjecture by Cerveau, which is like a dynamical characterization of projective spaces, which is like if X in Pn is a hypersurface, a smooth hypersurface, such that every foliation extends, then X is a linearly embedded Pn minus 1. Yes. With what I will tell you, I think I come and go. I don't know if we are close or not close to proving this, but there's something to say. The other one, the other motivation, is that I would say this a bit vaguely, but maybe you can define some, what did I use? Fol. So here I use the notation fol specifying x and L, no? So if I don't specify the x, it's because x can move too, yes? So maybe you have a space fol parametrizing pairs, no? A variety together with a foliation. And from here, you can project to the variety, no? Well, this is quite an interesting and huge topic of research. So it would be very nice if we could say something of these spaces by studying these spaces, no? Well, you can construct, I'm not saying, if you want it to be like a proper moduli space, it will be an algebraic space if things don't have. This guy? Yes. Ah, sorry. This is a quasi-projective variety. Because you look at, it lives inside So it lives inside this projective space, no? Because you are looking at the omegas. Quasi becomes from the open condition of not having zeros in codimension 1. And this is just a bunch of quadrics in the parameters of omega. And so if you have this situation, the question is like, let's call this pi. Is pi surjective? This would be like the first thing to ask, no? Well, I will stop here for a second. I'll say that what an unfolding is. So an unfolding, essentially, first I'll say a deformation, so a deformation of a foliation is essentially, we can do it over a small disk. And a deformation is over each point, no? I put a variety. And on each one of these varieties, I put, so we have xt or x0, f0, I have a foliation here, and I put continuously a variety and a foliation on each variety. Yes? Vaguely speaking, this is a deformation. Everything moves algebraically, let's say, or analytically. Now, there are some special deformations which are the following. Like, if X, the total space looks like this, and here I have my fibers of the map, then sometimes I'll be able to, like, I can pick a codimension 1 foliation here, no, an f bar, and when I restrict it to each one of these fibers, I get a family of foliations, no? Yes? So some deformation, I will be able to do this to construct the deformation as an intersection of a codimension 1 foliation with the fibers, sometimes, and sometimes I will not be able to do it. Yes? So this is the difference between a deformation, which is more general, and an unfolding. An unfolding is nothing else than I have a family of varieties, and in this setting, Y is the deformation, the total space of the deformation. No? I have a foliation on the central fiber, and I ask if I can extend it to the total space of the deformation. Yes?
Can't I have two unfoldings for the same deformation?
That's a special situation that tells you something about the central fiber of the deformation. You can, but I would say, in general, you don't. Okay, and so in this space, X and F, let's call it, let's imagine that the picture is like this. The direction, so here, a curve here will be a family of foliations, no? Of X and F. In this space, the unfoldable foliations, the unfoldable deformations give a foliation. And so I don't know, I have no idea how to, well, I don't know how to answer this question, but with this extension problem, we can attack the question of whether if the leaf passing through your particular foliation is a submersion to the space of varieties, no? So this would be, if I have a deformation of X, can I unfold my deformation along this deformation you gave me? Well, this is the version of this question that we can attack. Yes? Questions? Okay, so just to give an example, I will do a theorem of Gomez-Mont. Gomez-Mont says that, so X is a compact surface, and you have F a codimension 1 foliation with H1 X Pf equal to 0, and the singularities of F consists of points with, I will call it like this, multiplicity 1 and non-vanishing trace. Then I will come back to this, what this exactly means. But this is generic. Then every unfolding is trivial. What does this mean? This means that if I have my X over the disk So there's always a trivial way of constructing an unfolding, but it's not interesting. No, I just put the same f everywhere, and I put the horizontal. I interpolate the leaves like horizontally. No, so this would be I have x and my f bar, and I'm saying that this is isomorphic to x times c, and let's call it f times c. See? So there's an isomorph. So the family of varieties is trivial. It's just the same variety everywhere. And the foliation is putting the same foliation everywhere. Yep. So we will have like two sets of statements, both in the like embedding case and in the deformation case. Either something happens and all the deformations are trivial, or something else happens and you can extend in a number of ways. Okay, so now let's go to the local picture. So local picture. The good thing about like why this setting applies to both, well, because it just does, but it's because I think what you asked is that locally, an embedding, if everything is smooth, is exactly the same as a deformation. No? Because the normal bundle is trivial, and then, so locally, we have x is just Cn0. Inside, let's call it Cn times Ct0, no? And of course, this has a projection to C with variable t. And so we can see x as a central fiber of this like trivial family of small disks. No? Something that maybe is worth mentioning is that, okay, locally, now there's no line bundle anymore. So I have this, my omega in omega 1x, satisfying the integrability condition and not vanishing in codimension 1. And the question is now, does there exist an omega? Let's forget about the other one for a second, such that I star omega bar is omega. No. And the first, like maybe remark is that if we are at a non-singular point of the foliation, we know that locally analytically omega is dx, and so the answer is yes. No. And so looking at regular points give us nothing. The problem there is trivial. And we have to look at the singularities, right? So what kind of singularities, how do singularities like separate from this perspective? Let's take maybe the most common maybe that appears in geometry in general, foliation, which is, well, let's say omega is df. No? How can I unfold this guy? So I have to give this is f goes from x, let's call it to c, but so in coordinates I can put omega bar. I can say, okay, no, maybe f plus something depending on t, no? Plus t, for instance. No? So now I'm assuming, obviously, because of what I said before, that omega of 0 vanishes, so it is a singularity. This means that df in 0 is 0. But now omega bar in 0 will be, well, df in 0 plus dt in 0 will be just dt. No? It is non-zero. So we have a singularity. Here we have our copies. We have a singularity here, our 0. But we see that when we unfold it this way, it's not a singularity anymore. Yes? So what we are looking at is that the ambient space, the foliation in the ambient space, has a tangency with this guy. No? And so I would say the singularity is, in a way, artificial, or let's call it that the singularity is smoothable. We can choose an unfolding, an extension that smoothes it out. It disappears, right? On the other end, it can happen that Gomez-Mons statement, no? That all deformations, all unfoldings are trivial. And then it's the opposite, no? Like, it never disappears. But this is stronger. So, on the other end, we have, like, Kupka singularities. Essentially, a Kupka singularity is a singularity where, like, of course, omega of 0 is 0, but d omega of 0 is not 0. Around these points, essentially, the foliation looks like this. What am I doing? Like this. Looks like a smooth pullback from a foliation in the plane, yes? And so, for instance, it's obvious that if I extend it and this holds, then, and this does not hold, then when I pull it back to the central fiber, this does not hold either, because the pullback of 0 is 0. No? The pullback of d omega will still be 0. And so I'm not going to do the computation, but it's from this characterization, it's easy to see that Kupka singularities are rigid. Rigid for us will mean Gomez-Mons statement. So every time so say this is now Cn times Ct, t, and this is Cn, 0, 0. Every time I unfold it locally, I extend it locally, it has to be trivial. In some coordinates, it has to be trivial. Yes, this will be rigid. In the middle, of course, these ones do not disappear, but because I cannot do anything with them, no? All the things I can do are essentially nothing. This, on the other end, I can do too many things, and that means I can smooth them out. And in the middle, we will have persistent singularities. So a singularity will be persistent if every time I unfold it, it's still a singularity of the ambient space. Yes, of a foliation, of the extended foliation in the ambient space. So this does not happen. All right. So how would this look like? Well, a persistent singularity. Let's look at first order. No. So at first order, omega over at first order. Omega bar would be omega plus t some eta plus some h dt, no? Plus, I'm saying first order, t squared is now 0, yes? We are working on the first infinitesimal neighborhood of x in y. So if you do the computation here, you do omega wedge d omega. This gives you, well, omega wedge d omega plus t omega wedge d eta plus eta wedge d omega plus t squared d omega minus eta minus t which if I'm not mistaken, this is correct. And so for this to be 0, this has to be 0, and this has to be 0. This has to be 0. This is correct. But this is correct, no? No, this is correct. There you go. But you can see, let's call this 1 and 2. You can see that 2 equal to 0 implies that 1 is 0. Yes. And also, if you compute omega at 0, it gives you 0 plus 0 plus h of 0 dt. So if I want my singularity to be persistent, what this is saying me is that every time I write something like this that satisfies this equation, because this controls the integrability, the h you chose has to vanish at this point. Yes? It's like a very algebraic, non-geometric way of defining what the other thing I said, which is every time I unfold it, it has to be a singularity. No? So what we will do is, I'll go back here. Well, questions in the meantime? So I will define a sheaf of ideals, which will be like the h in OX, such that h d omega is 0 in omega 2x modulo omega 1x wedge omega. No. Why do I do this? Because every time, so if I know h d omega, I'm being silly, this is omega, wedge omega. If I know h d omega is omega wedge sum 1, and I know h, then I just construct the eta. And with the h and the eta, I construct the extension. And I want to point at the points that vanish at all their extensions. No? So these points have to vanish, these functions have to vanish at exactly these points. Yes?
Sorry, what do you mean by h in all x? h0 all x? Or the section or the general?
In that setup, this will be O Cn 0. But then I will take an x and do it locally on x.
So just going back to this classification, a curve singularity is a persistent singularity.
Yes.
But then
This is like,
we have seen that there may be singularity that when I deform, it's still a singularity but of another type.
yes. Yes. I will now make a picture. So the persistent singularities will be essentially the zero loci of this ideal sheaf. Yes? I promise what I said is true, that these are the singularities that when you deform, there's still a singularity. I hope I convince you with the computation, but that's essentially the case. And a few facts that now are quite interesting is that, so what Matthias asked is, F is rigid, no? I want to compare rigid with persistent, no? This is a very easy computation and gives you that. So a foliation is rigid if these two schemes, these two analytic spaces are the same space, no? This is for real, just you after the computations I'll show you, it's trivial. And then, so what's now an example of something that is, you can deform, but it's not rigid? Well, maybe, let's suppose we are in 4 dimensions, no? So I have something kubka, no? And something I did not say, I forgot to say, is that there's a theorem of Lagrange that tells you that if a singularity is small, then it has a local first integral. No? If it has codimension more than 2, it has a local first integral. And so in particular, small singularities are always on this side of the board, are always smoothable. In particular, they are not persistent. No? And so if I take something of codimension 2, which is kubka, which is rigid, and I add something smaller, so this will not be rigid, because the persistent locus is this, and all these points are not persistent, are smoothable. No? So this is not persistent. Not persistent. Yes? Okay. So something that maybe, for the sake of time, I will not write down, but is that, okay, there we did a first order approximation of the problem, no? We looked at the first infinitesimal neighborhood, and we saw that we defined what a persistent singularity is, but then you could go to the second infinitesimal neighborhood, the third infinitesimal neighborhood of this local situation. And you can ask yourself that, okay, I have a first order extension, so I have my h and my eta. Can I extend it to order 2? And this situation is way more complicated from a computational point of view. The equations are like very nasty. And so I will just say that a moment of honesty, I don't know how to handle this local computation completely. So I will sometimes put the hypothesis that if I can extend to order n locally, I can extend to order n plus 1. This will be what I call unobstructed, so I don't write it down. Unobstructed singularity is that I can extend it from order n to order n plus 1 always. This said, what we did, because we couldn't do that, is essentially look at a very long list of singularities and said, okay, we can prove they're all unobstructed. On the other end, I don't know a foliation that is actually obstructed. So if you know a foliation that you think is obstructed, you can tell me, I will be very happy. Maybe it's just a empty hypothesis. Okay, so what's the strategy to attack this extension problem, no? Well, as I said, we have x inside y. And what we did there already is we looked at the first infinitesimal neighborhood of x. No, this is Ox1, just in case is Oy modulo 2, and in general, xn will be n plus 1 n. So we have the first, the second, the third, and so on infinitesimal neighborhoods. In the limit, we take all the n's together. We will have the formal completion, no, like the Taylor series of x in y. So literally, like functions here are Taylor series of functions here with parameter locally with parameter t like that. And we will extend one step at a time. Yes? So we start with a foliation here. This will be our f0. And we will construct the f1, the f2, blah, 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 blah. At each step, we will see if we can extend, in how many ways. Yes? How do we do this? We do this essentially dealing with it as if it was a deformation problem. So sometimes when you do this, like Schlesinger type things, you get these statements. So proposition. We compute three things. The first one n minus 1, correctly, yes, is h0 x dx times nx over y. This is automorphisms of this guy that, or of xn, that restrict to the identity on xn minus 1. Yes? The second one will be the extension space of order n. I will say how this is. And the obstruction space. Okay. What does this mean? So these are the automorphisms of Xn that restrict to the identity on the smaller infinitesimal neighborhood. Okay? What do I care about this? Because I don't want to see automorphisms. So let's say you have y, and you can extend the foliation to y, but there is an automorphism of y that is the identity of x on x, so it doesn't change the foliation of x. I want to say that the extension you constructed and the change of coordinates by this big automorphism, I don't want to see the difference. Yes? So what I'm saying is that at each point, I don't want to see that difference. And this is exactly what the second space is.
So these are automorphism
Of y. So, but in order to say of y, I will do it infinitesimally at each step. And so the second space is, okay, suppose I can extend. You showed me one extension. In how many ways can you extend? A computation tells us that essentially this space parameterizes the extensions. More like precisely, this space parameterizes the actual extensions, and we are cautioning out by this guy because we don't want to see automorphisms. And the obvious question is, okay, well, when can you extend? No? Well, the obstruction space is this. This means that if you show me give me a foliation with this, in this part we need the unobstructed thing I said before. You show me an extension with unobstructed singularities. You make a computation that lies in this space. If this is the zero element, then you can extend. If this is not the zero element, then you cannot extend. Yes?
This is really the integrability.
Yes. Yes, yes. And so at each step, what I'm extending is the line bundle, no, because I start with a line bundle here. I promote a line bundle to higher order, and I extend the one form twisted by this line bundle in a way that when I restrict it to the previous step, it's the previous extension. No? Okay, questions on this that maybe it's me?
X1 is the tangent space of one of the moduli spaces you showed before. Not
X1.
without quotient, This is a fold.
Yes. Yes. Is the tangent space to the leaf? Remember that you had deformations that you can unfold and deformations that you can't. It's a tangent space to the leaf in that space, without this guy, no?
Without.
Yeah. Cool. So this takes a lot of work, and by invariance of difficulty, we should be able to prove stuff with these computations. What can we prove? So here I erased a statement of Gomez-Mont saying, essentially, okay, if you have a singularity, now I will rephrase Gomez-Mont's hypothesis. If you have a singularity with rigid singularities, a foliation with rigid singularities on a compact surface, then all the unfoldings are trivial. We will do both. We will do first we will do, you can always unfold in a non-trivial way, yes? And so deformations in this setting are particularly nice, no? Because a priori you look at this and it's a lot. You have for each n a different automorphism group, a different extension space, and a different obstruction space. But in a deformation, this guy is OX. And so this is not here, and this is not here. So this is just one space, one on each line that you have to worry about. No? Okay. So let's call it theorem 1. I don't know. Is that X compact manifold F codimension 1 foliation with unobstructed singularities. And we will require H1 of this equal to 0. Then F, let's call it unfolds or extends along any deformation Yes? So in particular, you construct a lot of things that are not in Commencement setting, because the conclusion of Commencement's statement was that, in particular, the deformation of X was trivial. No? Well, I'll just say it out loud in case someone is interested, but I think I have like 10 more minutes. Okay, just if anyone wants to do a computation, this statement is particularly cute when, so if you take f, a logarithmic foliation. I will say it in words, but essentially what you take is, if you take FIs to be sections of some line bundles, and you construct, the line bundles have to satisfy some hypothesis, and you construct this form, sum of, let's call it like this, lambda I dfi over fi, and if you want, you multiply by f1 fr. So with some hypothesis, this defines a foliation, no? And a logarithmic foliation that Javier will talk about in the next talk, I think. And the unfoldings of this guy, a priori you can say, okay, I have a lot of deformations. You move f and you move lambda in a way that it satisfies the integrability condition, and that gives you a lot of deformations. But the ones that are unfoldings is when lambda is fixed and you move just f. And when you compute this guy here, the obstruction to unfold, it gives you exactly the obstruction to extend the f, to extend the line bundle in the center fiber, each one of these line bundles to line bundles nearby, and extend the f's to f's nearby, so that with those f's you can construct this, you can do this construction fixing the lambda. Yes? So I don't know, I think this is particularly nice. Okay, so this is the deformation theoretic good affirmative answer to the extension problem. Now let's do the non-deformation. So now we have an embedding x inside y. Here, maybe. Here.
So in this case, y is
in the logarithmic one?
No, it is here.
No, x is a compact manifold.
And y?
And y would be, so I'm saying that every time you take a deformation of x, you can take that y, and it's positive. Okay, so now in the non-deformation statement will be, so now if x inside y is an ample divisor, same, no? F codimension 1 with unobstructed singularities. So now if the dimension of X is at least 3. And this sheaf is ample, then F extends uniquely. Yes, so this, one of the papers I mentioned at the beginning of Mateus Figueira is the one with Y is Pn and X is a hypersurface, a smooth hypersurface. He proves essentially, I would say, the same statement without this hypothesis. Yes, without the like, I'm having to say something about the singularities at the cost or at the other way around in order to put any Y. No, I still don't know a foliation with obstructed singularities. But okay, so, and if you say, okay, but this is a condition that holds, of course, we need the singularity to be unobstructed, the singularities to be unobstructed, but it's not saying much of the geometry of F. You can be a bit more subtle if you want. It would take a bit more effort doing some computations, and you need positivity of this guy. Okay. So I would say the proof with the hands is that we come here. So from the ampleness, we get that this guy is 0. Yes, this is called a vanishing exercise. And then once this is 0, you know you can extend up to here. No? When you're here, you need some convergence now. No? And that's, so sorry, in the first ample, I meant that sheaf is ample, no? NF times NX minus 2 is ample. And now, when you have a smooth Y, No, X is smooth. When you have, if X has dimension at least 3, and the normal bounded is ample, then you have a Lefschetz condition that tells you essentially, like the very fancy way of saying it is that if you take the limit of the U containing X and you look at vector bundles of or sheaves on U, this gives you this. No? This is a very compact way of saying every time you have some functorial construction here regarding coherent sheaves, you can, there is some actual neighborhood of X in Y where you can make this non-formal, no? Like positive, the positive dimensional in the normal direction. So this is to say we did already a lot of computations here, and now we are relying on strong theorems to not do the computations for the conversions. Yes? Okay, so this is positive answer. And so what are examples? So this is uniquely, no? And what are examples of, well, places where this does not hold? Well, if you take Pn minus 1, like we said before, like Servo's conjecture in Pn, you take a point, you project, here you have your foliation, and you project. You take, so this is a very bad drawing of a R is a linear projection from Pn. You pick any linear projection, you pull back, and you get an extension. Yes?
So how your assumption rule out this?
This, I think this does not hold for degree considerations. No? No?
The normal of X over Y is all 1. You just take something that's high enough.
But NF will be positive, no? And then 1 minus 2 times something positive will be negative. Ah, you're right, my bad, I wrote it the other way around. Sorry, my bad. My bad. Okay, and so essentially, thank you. This is the picture. So in the rigid situation, where the singularities are rigid, this is what is happening. So let's write that down. So let's write it now, theorem 3. We will call this a tubular neighborhood. Yes, a tubular neighborhood will be like some U in Y containing X with a retraction U to X such that R restricted to X is the identity. This essentially is very rare to have a tubular neighborhood of something inside something else, even more if everything is algebraic, no? So we can prove in a very nice, I think, way, because we already did all the computations there, is that so X has to be smooth, again, projective of dimension at least 3. If H1 of TF n x over y minus n is 0 for every n. F codimension 1 foliation, and the singularities of F are rigid, then X has a tubular neighborhood. And the extension is, let's call it R star, is unique unless X inside Y is Pn minus 1 inside Pn, linearly. Yes, so what is this saying? Why this is a thing? Existence of tubular neighborhoods are rare. The statements that show existence of tubular neighborhoods essentially ask Tx times the normal, so the same space but with an x instead of an f to be 0. This is done by Fujita and Griffiths. And so we have a map from this guy because of the exact sequence defining the foliation. You have a map from Tf to Tx. So you have a map from this H1 with the f to this H1 with the x. And what's quite cool, I think, is that Fujita and Grauert, by separately, prove that the obstruction, if you want to study the problem of constructing a tubular neighborhood, the obstruction, so the equivalent of this space, will be the H1 with the Tx, no? And what is nice is that with this hypothesis, so if everything is rigid, the singularities are rigid, the obstruction to, and this holds, the obstruction to extend the tubular neighborhood at each step maps injectively to this space. No? So this is saying you that you constructed the tubular neighborhood up to step n. In step n, you already have an extension, no? Because you can pull back via the projection. So you have one extension. And you ask yourself, can I extend this foliation to the next step? Well, if you can, it's because you can also extend the tubular neighborhood. Yes? This is what that statement is saying. And in particular, this should be telling you a lot of foliations that do not extend. And this is why it's close to the Servoz conjecture, but I don't know how close. Because tubular neighborhoods are too rare. No? Like a hypersurface in PM does not have a tubular neighborhood unless it's a linearly embedded projective space. Okay, I will just write one more thing and finish, which is the deformation. So we had affirmative for deformations, affirmative for embeddings. Now we have sort of negative for embeddings. And the negative for deformations would be the higher dimensional version of Commence-Mons statement, which is like X compact manifold. With an F, a codimension 1 foliation with rigid singularities. And H1 of TF is 0. Then every unfolding is trivial. So this is the same conclusion as Gomez-Mons. No, that if I have a deformation of the variety where I can extend the foliation, then the deformation of the variety is trivial, and the extension of the foliation is also trivial. And it's nice because the proof, essentially what you show is that the deformation has a tubular neighborhood. X has a tubular neighborhood in its deformation, and then the deformation has to be trivial.